Hello everyone. Welcome to this today's lecture. So today I will be doing GATE 2019 question number 39 to 40 and 46. These are the organic chemistry, as I have been taking classes only for the organic chemistry. As I said before, the idea is not to solve the question but to understand organic chemistry in toto, right? So let's start with question number 39. The first question says the major product formed during the following reaction is. So you are having this molecule and you are adding PCC and zinc bromide. So when you think about PCC, what comes to your mind? It is a mild oxidizing agent which converts primary alcohol into aldehyde and stops there. If you put little more powerful oxidizing agent, it will convert alcohol into aldehyde, and then it also converts aldehyde into carboxylic acid. But if you want to stop there, you use PCC, that is pyridinium chlorochromate. Okay. Now, there's by mistake I wrote reducing agent. It's a oxidizing agent, right? And there are very few such reactions which does this job, that which stops primary alcohol of oxidation of primary alcohol to aldehyde and doesn't go up to carboxylic acid. Some of them are Swan oxidation, then Des-Martin, pyridinone, and things like that. And then we have ZnBr2 in the second step we are adding. So what is ZnBr2? ZnBr2 is Lewis acid. Its octet is not complete. So it will accept lone pair of electron from aldehyde which is being formed, and then it will help to carry out reaction something like Friedel-Crafts alkylation, Friedel-Crafts acylation kind of stuff. Okay. So let's go step by step. So you are having this molecule which has a stereogenic center. So CH3 is away from the viewer, so of course hydrogen is towards the viewer. And the first step you are adding PCC, so you are oxidizing it, so the alcohol becomes aldehyde, right? So the alcohol becomes aldehyde. Now what happens when ZnBr2 is there? So ZnBr2 is a Lewis acid, so this oxygen gives its electron pair here, and zinc gets negative, oxygen gets positive. Now the electrophilicity of this carbon has dramatically improved. Why? Because oxygen is already electronegative. It pulls electron from the carbon, the pi electrons from the carbon towards itself. So positive polarity was there. Now oxygen has got positive charge. So its electronegativity is dramatically increased because now it wants more and more electron, and therefore now this reaction can happen. So electron rich center will attack. Which is the electron rich center? Electron rich center is of course this pi bond. Pi bond has lot of electrons, weakly held electrons, because pi bond is not very strong bond. Okay. Now two possibilities are there. One possibility is there. You understand what happens here is, it has a p orbital here, it also has a p orbital here. Both of them have 1 electron. Both of them have 1 electron. Now this can take, sorry, I should have done like that. Yeah. So this can take both the electrons and go and attack here, so that you get a positive charge here. Other way will be this p orbital takes both the electron and attack there, and this one gets positive charge. So imagine if the attack happens from this side, then what happens? You get something like this intermediate. So when you attack from this side, you are getting 7-membered ring. Now remember, 7-membered ring is neither kinetically nor thermodynamically favored. Very unfavored in kinetically. Thermodynamic also is not stable. So 6-membered ring would have been favorable. So if attack happens from here, it would have been 6-membered ring. So that will definitely be favorable than this. Apart from that, if you see here, you are getting a carbocation on secondary. You are getting secondary carbocation. Here one hydrogen is there, right? Because attack happened from, just see here, attack happened from this side. So here one already hydrogen was there, so you are getting a positive charge here. So again secondary carbocation is not stable. If possible, it will go through a tertiary carbocation intermediate. That is kinetics. Kinetics talks about the stability of the intermediate. So if an intermediate is more stable, then the reaction goes faster. So that's what happens. So attack will be from other side because it will give tertiary carbocation. So that means kinetically favored, and also it gives you 6-membered ring, that means thermodynamically favored. So attack happens from this side, so you get a positive charge here. Now look here on this carbon, all three are substituents. So it's a tertiary carbocation. Tertiary carbocation, you know, is stable because three substituents are there. All three of them pump electron and it stabilizes the positive charge. And then you get O, Z and Br. Now zinc, you know, zinc having positive polarity, oxygen has negative polarity. Why? Because very clearly, I did not draw here. Okay, so negative charge is there, but basically here it becomes like that. So it becomes neutral. Oxygen becomes neutral here. But at the end, polarity difference is definitely there. So let's move out. And then what happens is this oxygen goes and attacks this proton. So that becomes OH. And this moves in and you get a double bond. Till here it was very simple reaction. So why they gave in gate? Because they want to look at the stereochemistry of the product formed. So let's see the stereochemistry of the product formed. Now look here, this pi bond has to attack. CH3 is away from the viewer, which is bulky compared to CH. H is not that bulky. So what happens? The attack will happen from outside the screen. Okay, it is coming from towards the viewer because CH3 is away from the viewer. So it pushes this OH, which forms finally OH, behind, and this part comes front. So basically what you get is OH behind and this part has come front and this part is front. You see this attack is happening from front, this is also front. So you are getting this product. So the answer is C, right? Moving on to the next question. In the following reaction, the major products P and Q are. So this is very simple reaction. This is basically generally we use MCPBA. So phenyl ring is there, so metachlorobenzene they use, and it is MCPBA, metachloroperbenzoic acid. It's not COOH, it is COOOH. So it is used either for epoxidation or used for Baeyer-Villiger oxidation. So very clear cut, because here double bond is there, it will undergo oxidation. And this OR is toward the viewer. It does not matter actually, you can always rotate the molecule, it will be toward the viewer, but then it gives a pair of enantiomers. Right now it is toward the viewer, okay? And in one position this R is having H, instead of R basically it is OH, that's alcohol. In another case you are having COET, so it is ester, O, C double bond O, ET. So we have to find out what's the product formed, right? So basically in this one, the pi, the alkene, they have this pi bond, the HOMO, the filled electrons, they go and attack on this oxygen through its anti-bonding orbital, and it basically undergoes epoxidation. So how it happens is something like this. This pi bond goes and attacks here because this is electron rich center and this is electron deficient center. Therefore, HOMO of this and LUMO of this interacts. So this goes and attacks here, and then this bond comes here and this bond takes a proton, so that you get oxygen minus charge, and this goes and attacks here and you get epoxidation, and this comes out as carboxylic acid, right? Now what happens is generally it is very stereospecific. So if a bulky substituent is there, see this COET is quite bulky, it is towards the viewer. So the attack will happen away from the viewer. So because this is coming out of the screen, COET is coming out of the screen, this this superacid will attack from behind the board. It is from away from the viewer, and therefore you get epoxidation away from the viewer. But when OH is there, it forms hydrogen bonding with this peroxy acid. So this forms hydrogen bonding. So because OH is toward the viewer, so it brings this molecule, this peroxy acid, front of the screen. So attack is from the top. And then what happens? Then this pi bond goes and attacks here, this goes and attacks here. So it is coming from the front. So it is thermodynamically unstable but kinetically favored, and therefore you are getting this product. So remember, if you have something like OH and sometimes even NH2, so they will guide the reaction in one particular way. So the answer is B, okay? Moving on to the next question. So you are having alpha beta unsaturated ketone and you are having Gilman's reagent. So whenever Gilman's reagent is there, you understand this is a soft base. So it will go always under attack on the soft electrophile. It's a soft nucleophile rather than base, soft nucleophile. So it will attack on the soft electrophile. So it always undergoes 1,4 addition. And then you are using PHSCBr followed by oxidation. All these are very simple reactions. You will get it very soon. No stereochemistry also involved. So this is one of the easy questions they had given, right? So all this I have told many times. So yeah, little bit I will just tell you why carbon is more, why electrophilic attack, nucleophilic attack always happens on carbon. Something like this is there. Okay. Why nucleophile always attacks carbon and not oxygen? Why it never happens, it attacks oxygen and this bond comes here? The reason is this: carbon is less electronegative than oxygen. So if you compare the atomic orbitals, oxygen atomic orbital is lower than carbon. So now two atomic orbitals are there. We are talking about the p atomic orbitals. P orbital is there, p orbital is there. So they form two pi molecular orbitals. One is bonding, one is anti-bonding. Both of them give 1 electron. Both of them give 1 electron. So both electron comes here. This is HOMO and this is LUMO. Or rather I should say this is bonding molecular orbital. This is anti-bonding molecular orbital. So this is vacant. So nucleophile always attacks on anti-bonding orbital. Bonding is through bonding molecular orbital. Anti-bonding is where nucleophilic attack happens. So nucleophile attacks here. You see this anti-bonding orbital is closer towards carbon. Its energy is closer towards carbon. Therefore nucleophile always attacks on carbon. So this is a molecular orbital approach of it. And so that's why, you know, always when we talk about SN2 reaction also, let me show it to you. Something like when we talk about CX is there. So bonding orbital is front, anti-bonding orbital which is 180 degrees. So therefore nucleophile goes and attacks from behind, and therefore you get inversion of configuration. This leaves and nucleophile attacks from the that side. So attack is always at the anti-bonding molecular orbital, right? Moving on. So you know this basically the most of the positive charge on this carbon because it is directly attached to oxygen. But here also certain positive charge is there because this comes here and this goes up and you get negative charge here, you get positive charge here. So basically certain amount of positive polarity is on this carbon also, and therefore nucleophilic attacks here happens here if you are having soft center. Why is it soft? Here what happens, the pi bond is between carbon and oxygen. Oxygen is electronegative, so it pulls the electron towards itself. So this lobe gets shrunk, so tough to polarize, so it is a hard center. Whereas here it is p orbital. So p orbitals are much bigger, okay? It's not attached directly to oxygen, but between two carbons. So they are much bigger. You can polarize them, so it is soft center, okay? Moving on. So you are having R2CuLi. So this is soft because of copper, no? This is soft. So it will attack on the soft center, Gilman's reagent. It will always give you 1,4 addition. So this CS3 minus goes and attacks here, you get here and you get here. Now next step, if you would have given proton, if you would have given added of some acid aqueous mixture, you would have done some workup. Immediately this would have come down and you would have got back your ketone and this proton would have been taken away. But here you are not adding proton, rather you are adding PHSCBr, right? So since you are adding PHSCBr, so sulfur is electron deficient. Here bromine is attached. So this bromine can leave. You understand? Bromine is electronegative. So bromine had negative polarity and this one had positive polarity because bromine pulls the electron. Sulfur happily undergoes this nucleophilic attack on it. So this comes down, this comes and attacks here and you're getting this. And next step you are adding H2O2. H2O2 basically oxidizes. It forms selenium oxide, and this one has a 2 resonance structure basically. So it's like, you know, Sc plus is there and O minus is there. It comes out, electron comes out here and then this comes here and this goes away. So selenium is lost, it becomes selenic acid and you get alpha beta unsaturated ketone. So it's very simple, you just look at it. First selenium attack, then you had oxygen. So this oxygen has negative polarity quite a lot. Compared to selenium, oxygen is more electronegative, so it pulls electron towards itself. So this goes and attacks this proton on the neighboring, and then this gets in, and then this eliminates out, and you are getting this alpha beta unsaturated ketone. So that's what it is, and you get this product B. Right? Moving on. Next question is, you are having pyridine N oxide, ortho position you are having CH3, and you are reacting with acetic anhydride. So this was bit tough question, but I saw this question directly, it was taken from Claydon. Not even a methyl group has been changed to ethyl group or something like that. So we will do this, but before that let's understand why we talk about this pyridine oxide, pyridine N oxide. It was a wonderful molecule, whoever discovered it. Lot of things which was not possible to carry out on pyridine, you can do it after you make pyridine N oxide. So how do you make pyridine N oxide? Just react with perbenzoic acid, something like MCPBA. You get this. Now pyridine had nitrogen. So nitrogen, you know, electronegative, and this lone pair also is parallel to this screen, whereas this p orbitals, this pi bond p orbitals are perpendicular. So they are orthogonal 90 degrees to each other. So there is no overlap. So it does not give electron to the benzene ring. Rather it pulls away all the electron. From the benzene ring towards itself. Therefore electrophilic attack, if you think that like benzene, some electrophile will come and pyridine will attack, it's very, very tough. And nucleophilic attack also becomes very, very tough. But once you make pyridine oxide, it's like magic. It starts happily, very fast. It will undergo both nucleophilic attack and electrophilic attack. How? Let's see. What happens is oxygen is having minus charge. So this oxygen minus charge, it pumps electron here. So on the ortho position you are having electron density. Also it can happen on para position. So both on ortho and para position this electrophilic attack can happen. So you can carry out this reaction, then this oxide can be very easily lost. That also I will show later. So when you want to carry out electrophilic substitution at ortho or para of pyridine, immediately just react with perbenzoic acid, make it an oxide, and then oxygen has lone pair, this pumps electron, and then this you can see the resonance. So you get electrophilic attack on either ortho position or para position. You will get both and you can separate them out. Nucleophilic attack also, it can happen both on ortho and para. Why suddenly it is much more better? On pyridine also it can happen, but here it will occur much better. Why? Because nitrogen having positive charge now. So it pulls the electron strongly. So this comes out here and the nucleophile can attack, and it becomes much faster than normal pyridine. You can carry out this nucleophilic attack on it. And then finally you want to get rid of this O minus, because you want to carry out all those reactions on pyridine ring. So just react with PCl3, happily it gets out at POCl3 and get back your substituted pyridine. Okay. But in this question it was bit different. So here when you attack with acetic anhydride, this O minus goes and attacks. So unless you have seen this question, no, it's tough, you will not be able to solve. So if you want to crack GATE, or rather anything, JRF or JAM, 2 organic chemistry book you have to just drink it. One is organic chemistry by Claydon, another is organic chemistry by Caruthers. You can buy it, they are interesting books and wonderful book. And so this question is bit different than normal reactions what happens in oxide. So this O minus goes and attacks here. Otherwise you would have thought that because it is electrophilic attack it should happen on the ortho position, that's what we will think. But here O minus attacks, so this is what they saw in lab, and you get this. And then what happens is this CH3, this proton is bit acidic because this negative charge, carbon, the conjugate base negative charge will be stabilized by resonance because of this N plus, and therefore even a weak base like acetate ion takes away this proton, this comes down here and you get this product, and then this undergoes, see again they would have liked to get back your aromaticity, but here what happens, immediately it undergoes 3 sigmatropic shift. So 3 sigmatropic shift, 3 plus 3 6 electrons. So 6 electrons are there in the transition state. So reaction happens under thermal condition. It is symmetrically allowed under thermal condition, geometrically also allowed. So counting, how do we count? Wherever the bond is breaking, see here, this bond comes here, this bond comes here, and this comes here. So this is one of the pericyclic reaction. So bond is breaking here. So start counting from both the sides. So 1, 2 and 3. Here also you count 1, 2 and 3. So the bond, when bond formation happens, bond is forming here. So here both of them are having the number 3 3. So you have to number it as 3 sigmatropic shift. And so this comes out here, you get a double bond here, nitropyridine comes back, you get back the aromaticity, and therefore it happily undergoes 3 sigmatropic shift. It is a normal pericyclic reaction under thermal condition. Okay, look at it, it's very simple. That's it. So that is answer is, oh, I think by mistake I wrote D. It is answer is C. Okay, so this was mistake. It is C. Fine. Moving on. The last question. The specific rotation of optically pure R2-bromobutane is minus 112. So here R was levorotatory. That means S is dextrorotatory. So now if R is having rotation of minus 112, that means S will have plus 112. You can think is levorotatory 2-bromobutane is L 2-bromobutane is minus 112. So D dextrorotatory will have plus 112. They are exactly one and the opposite. It says you are having a sample which has mixture of both R and S, and the rotation is minus 82.88. So what is the percentage of S enantiomer? Okay, so it's very simple question. So you are having R butane, so value is minus 112. So if you are having S, it will be plus 112. Now both are present. So imagine if S is present X, because they asked for S, that's why I put it X. You can put R also as X, does not matter. So they have asked what is percentage of S. So I have put S as X. So R will be 100 minus X, because percentage out of 100. Out of 100, if S is X, so R has to be 100 minus X. If you imagine if S was 40%, so 40 is there. So how much is S? R 60%, 100 minus 40. So now what is the specific ratio? Specific ratio of the mixture is minus 82.88. So X percent, R is X percent, okay? S is X percent. So X percent of S, right, S enantiomer. So S is having the optical rotation of 112. So X percent of 112 plus 100 minus X percent of minus 112 should give you the value of minus 82.88. So when you do this, then after this all very simple. You take out 1 by 100. So it becomes 112x. Here it becomes 100 minus x into minus 112. So that will give you this, and you get this. You solve it and you get your x. So 13. So 13% of S was there, right? So that's it for today. Thank you very much.